Everyone, my name is Yuan Yang from Vanderbilt University, and I'm going to talk about our work on the Raven progressive matrices. We studied how different analogical constructions affect the performance of the computational models. So here are two examples of the Raven progressive matrices. On the left is a 2x2 example. On the right is a 3x3 one. And the test taker needs to select one option from below here that best fit into the matrix above here. So here is an overview of our system. We first take the scanning image of the test problem from the booklet, and then we cut the scanning image into smaller images where each smaller image represents an individual matrix entry or an option. And then we feed this smaller image into our model, which is composed of three important components: the integration strategy, image transformation, and the analogy. And it will output the answer choices. We consider our system as a visual imagery reasoning system, which means we represent the problem as pixel-based images, and then all the reasonings are done through quantitative transformation over these images. One important piece of many of our image-based models is similarity metric, how you compute similarity between two images. We use variations of the J-card index to calculate the similarity, including a way to obtain the similarity under different relative translations of the two images. So our first important component, transformation, we have two dimensions to describe a transformation. A transformation in our system can be either a unary one or a binary one. By unary, I mean this transformation takes a single input image, while the binary one takes two input images. And we use also affine transformations or set operations. For the unary affine transformation, here are some examples. We consider only the rectilinear rotations, reflections, and the combination of them. And a unary set operation takes a single input image. Given two parameter images, it outputs the images in the last column in the table. The parameter here is used to derive informations, relevant informations for us to allow us to apply the transformation onto the input image. For example, let's say the first transformation here at div. We first subtract A from B to get the difference between A and B, and then we add that difference on C. That's how we get the answer here in the last column. And in the a binary set transformation takes two input images, and given a single parameter image, it outputs the transformed image in the last column. The parameter image here is mainly used to align the input image. For example, the first one, the unite transformation, we want to unite A and B, but there are many different ways to align A and B. So the parameter image C here just gives us that instruction to help us align A and B to get the desirable answer in the last column. The second important component in our model is analogy. Again, we have two dimensions to describe our analogies. Analogy can be either a simple analogy or a recursive analogy. And the analogy can also be composed of pairs of images or 3 tuples of images. So for simple pair analogies, given the matrix here, we can easily derive the row analogies here on the left. A is to B as C is to the missing entry. And similarly, in the vertical direction, column analogies is to C as B to the missing entry. And very similar to the simple pair analogy, simple 3 tuple analogy, we also have the row analogies here and the column analogies. Recursive analogy. A recursive analogy in our system is composed of 2 or more simple analogies, where each simple analogy represents a subproblem. So for example, let's say this one, this recursive analogy on the left. The first simple analogy in it represents a subproblem of this analogy with F as the only option to choose from. The second simple analogy represents a second subproblem, but with the original options from the Raven problem. And likewise, we can do the same decomposition in the column direction to get the recursive analogy here on the right. And we can do the same thing to derive our recursive pair analogy. The difference is a pair is smaller than a tuple, so we can even include more subproblems in the recursive pair analogy. So for example, these 2 matrices on the right. To solve more, almost all the problems in the standard Raven progressive matrices, we do need more analogies. So we expand the original matrix by copying the matrix entry in a cyclical way, so that the local spatial relation in the original matrix is preserved everywhere in the new expanded matrix. And then we encompass matrices with quadrilaterals of different shapes. The intuition behind this is that different shapes of quadrilaterals correspond to different spatial relations between matrix entries. And then we do the same thing on the 3x3 matrices to expand it to derive more and more analogies. Now, given the analogy that relate the individual matrix entries and the transformation, and the analogy that suggests which set of matrix entries to relate, how might intelligent agents solve the Raven problem? Let's take the 2x2 problems as an example. We first try to explain the matrix with pairs of analogy and transformation. And then we try to verify our explanations with the options. At last, we make our decision on which one to choose. So for this 2x2 example, it can be solved by this explanation in bold with the additive transformation with this simple analogy. A is to B as C is to the missing entry. Similarly, for the 3x3 example, it can also be solved by the same 3-step process. To solve it, we need to use this explanation here with inverse unite and a recursive analogy. So we need to quantify this process. We design the 3 score functions corresponding to the 3 steps in our process, and these scores are purely based on the similarity matrix we mentioned above. So, for example, for the first step, we have the MAT score, which actually measures how well an analogy and a transformation can be used to explain an incomplete matrix. And for the second step, we have this O score here. It actually measures how well an option fits into the matrix given the analogy and the transformation. And the third score for the third step is simply a weighted average of these other two scores. So given this functional dependency of scores and being inspired by some of our own introspective observation about how we humans solve the problems, we have a very useful heuristic, which is ideally a good MAT score implies good O scores, and that's good MATO scores. This heuristic is actually, imagine that if a human test taker has a perfect explanation of what's going on in the matrix, this taker will just use that explanation to select the option without considering any other possibilities. So this is actually what this heuristic is saying. Now, given the heuristic and the functional dependency, we again have two dimensions to describe our integration strategies. So a strategy in our system can be from completely ignoring the heuristic to completely relying on the heuristic. And in terms of the scores, a strategy can optimize either the MATO score or the O score. We can optimize the O score because the O score also depends on all the variables we define here. So for the first one, we call it M-confidence strategy. It tries to optimize the MATO score, but before that, it first optimizes the MAT score to get the best explanation represented as a pair of an analogy and a transformation, and then optimize the MATO score over the option. And M-neutral strategy, it also first optimizes the MAT score, but only over the transformation. And then, given the best transformation, it further optimizes the MATO score over the analogy and the option. The MATO, the M-prudent strategy here is just a brute force search over all the possibilities of analogies, transformations, and options. And O-confident strategy, optimizing the O score, is mathematically equivalent to M-confident strategy because the MATO score is simply a weighted average of MAT score and O score. So we don't have an equation for that. And like the M-neutral strategy, the O-neutral strategy first optimizes the MAT score over the transformation, and then optimize the O score over the analogy and the option. And the O-prudent strategy is simply another brute force search over all the possibilities, trying to optimize the O score. We tested all our strategies on the standard ribbon progressive matrices. This test has 5 problem sets, A, B, C, D, and E. Each of them has 12 problems, so we have 60 problems in total. On the left is the M strategies. As we can see, there's no big difference between the performance of these strategies. On the right is the O strategy. The O-confident strategy has the same performance as the M-confident strategy because they are mathematically equivalent. And for the other two O strategies, they contrast sharply with their counterparts in the M strategies. And in particular, the less it relies on the heuristic, the worse its performance is. Yeah. And if we plot all the answer choices of these strategies on a 2D plane of MAT score and O score, we can see the distribution of these solutions. On the left is, again, the M strategies. As we can see, all the data points are located near the diagonal line or above the diagonal line. Whereas on the right, for the O strategies, they are many of the data points are above the diagonal line or even located far away from the diagonal line. So considering the performance between M strategies and O strategies, the difference between their performance and the physical meaning of M score and O score, we have a hypothesis that to design an intelligent agent or model to solve the standard ribbon progressive matrices, we need to consider more about how to explain or understand the matrix rather than finding a good match in the options. Besides comparing strategies, we further studied the influence of transformations and analogies. We first group our transformations into 4 groups. The first group is the affine transformation. The second group, the diff group, includes all the transformations that manipulate the difference between images. And the third group, match group, include duplicate and rearrange. The last group include all the other set operations. And we also divided our analogies into 4 groups here according to the shape that is being used to derive these analogies. We first, using the M-prudent strategy, we first put the comparison in a one-to-one way so that we can see the strengths and weakness of each analogy group and the transformation group. So for example, here, the S analogy group and the diff transformation, they can solve most of the problems in problem set A, B, and C, whereas most of the problems in problem set D and E can be solved by the R analogy and the set operation. Furthermore, we put this comparison in an incremental way by gradually adding more and more analogies and transformations into our model. As you can see, there are monotonical increases in both vertical and horizontal direction. But the increases in the vertical direction is much more significant than the increases in the horizontal direction. This is because we start this with S, and S is the most powerful analogy group, as you can see in the one-to-one comparison. So I believe if we define this analogy group at a finer level, we can see more significant increases in the horizontal direction as well.
3 minutes.
Yeah, thank you. After I finished this work, I started to reflect on why I use analogy to solve this problem, solve the ribbon problem. So tests like ribbon, what characteristics do they have? They are designed to test the fluid intelligence, especially adaptive ability, which allows us to make sense from the new situations. So ideally, the scenario included in this test should be as new as possible to their test takers. Now, the question is, if this is completely new to me, how do I know I'm solving the problem correctly? I personally think that the answer lies in the redundancy. There must be some clue from the test designer to tell the test taker what is wrong, what is right. And redundancy is just such a common way to communicate this information. And at the same time, analogy is just such a useful to organize redundant information to give us that aha moment in the test. And the further question is, how can an intelligent agent discover these organizational patterns and the integration strategies on its own? So I guess this brings me to the end of my presentation. Thank you for being so attentive, and I can take your question now.
Thank you, Yuan.
Thank
There
you.
are a few questions on Slack. This one is by Chris McGreggor. Is your model an account of how you think humans are solving these problems? Or a rational account of how an intelligent agent might solve these problems?
Yeah. Personally, I think I think the implication of this work is twofold. For the to design an AI agent to solve the problem, it should be the analogical ability is an unavoidable issue, considering the nature of these tests. And for a human, I think this work just serves as another demonstration of how analogical ability contributes to individual difference in these tests.
Okay, let me go to John Laird's question, and we can come back to Chris McLean's. Then I'll follow that up with Matt Clank's. John Laird's question, I think, is more closely connected with Chris McLean's. John asks, have you compared your results on different strategies to human performance? Probably looking at percentage of questions that a group of people get correct, based perhaps on problem difficulty.
Oh, actually, we did compare our data, the performance of our computational model to human data, but you know, the page limit of the paper, we didn't include that result in the paper.
But can you share the main result as you compared it with human data?
Oh yeah, let me just find that graph. I think I can find it now.
You can also just share it as a summary, as just a 1 sentence, 2 sentence summary.
Oh yeah, I just put a graph on the shared screen. Can you see it?
Yes.
Yeah, this is how we compare our data with the human data. The human data is from age year 6 to year 19, I think.
Okay, and so this tells me that your program is doing about as well as what, about 15-year-old?
Yeah, about 15 years old.
Okay. Just to go back to Chris's question for just one more second. So given this comparison, you want to say, and perhaps you don't, and that's perfectly fine, whether this is a account of how humans are solving the problems, or is it still a rational account of intelligent agents might solve the problem?
I'm sorry, I didn't quite understand that question.
Okay, so one can think that the techniques that you have developed are techniques for building AI agents that can solve problems of this particular class, but they are not intended to be a model of human thinking. Or alternatively, one can take the position that the models that you're developing are actually models, or at least intended to be models of human thinking. So that's the
Yeah, I think our model is not designed to simulate human thinking, because for example, for this for example, for the way how we derive our analogies, I don't think any human will derive an analogies in this automatic way. Yeah, so we're not trying to exactly simulating the human thinking.
Okay, so behaviorally, it might compare well with what human performance is, but from a cognitive perspective, you're not making any claims about human thinking, which is just fine. Let me move on to the question by Matt Crank. How do you think about generalizing this approach to other kinds of visual problem solving?
Yeah, well, one of our undergoing research is trying to go beyond the proportional analogy. Like the proportional analogy is there just so intuitive, so simple. We're trying to add more attributes, properties into this analogy, or to describe this analogy in a multidimensional space, so that we can study it in a larger application area, including other visual spatial reasoning, analogical testing tests. So that's a way. That's one of the ways to generalize this work. Of course, there are many other ways. Yeah.
Okay, let me read one comment from Ken Forbes. This is perhaps more a comment than a question. You can comment on it if you want. In regard to how one knows that one is solving the problem correctly, that's the question you're asking. His answer is high similarity fit in the constructed solution. So does that make sense?
How one knows that one is solving
the problem
similarity fit.
Yeah, that the constructed solution has a very high similarity fit.
So for this one, I'm thinking about what similarity here refers to, because similarity can be used to refer some similarity of appearance or similarity of relations. So if here it refers to relations, I think it's somehow equivalent to the redundancy I mentioned in that slide. Yeah, I don't know. Maybe I'm wrong.
So that's good. We'll have to stop here, Yuan, but there are several other comments from Ken Forbes and